I'm going to do another example of our fundamental theorem of algebra. So here's example 1b here. I want to find all roots of my equation, x to the fourth plus 2x cubed plus x squared plus 8x minus 12 equals 0. I noticed a couple things here. The first thing I notice is that my degree is 4, which tells us, with our fundamental theorem of algebra, we have 4 roots we're looking for. Okay, I have 4 roots. Now, I also notice I have 5 terms. We don't know any way to solve or to factor something with 5 terms. Factoring by grouping, we need an even number, so that's not going to work. Let's go straight to our rational root theorem then. And list out our possibilities for our numerator and for our denominator. Possibilities for the numerator have to multiply to 12. So we could have 1 and 12, 2 and 6, or 3 and 4. And for our denominator, numbers that multiply to my leading coefficient, which is only 1 or negative 1. It's really, in this case, my list of numerators is really my list of possible. My list of possible rational roots. Since all of these would be over 1 anyway. Now to check this, I'll go to my calculator. Y equals, type it in, x to the fourth plus 2x cubed plus x squared plus 8x minus 12. And we'll check. And I guess I actually have some x values in here already, but we'd run through and check the ones we have. 1, turns out, is one of my rational roots. 1 is one of my rational roots. Okay. We also see here that negative 3 is 1. So I'm going to write that down. It'd be silly for me to not write that down. But after that, I don't know if my other roots are rational or if they're irrational, if they're complex, what is going on there. So once I find one of my rational roots, let's use synthetic division and see if I can find the rest. I'm going to do synthetic division with my equation. And since 1 is a root, that's what goes in my box here. Then across the top, we write our coefficients. 1, 2, 1, 8, negative 12. Make sure when you're doing synthetic division, this first number you bring down. I've seen quite a few people writing a number here. We don't have a number here. That's just bringing my first number down. So bring that down. Take 1 times the number in my box and add. Times the number in the box, add. 4 times 1, we'll get 12. 12 times 1, we have a remainder of 0. Now, since we know that 1 is a root, if you ended up with a remainder, that's your clue something went wrong somewhere along the way. And that's our remainder. These are our 1s. These are our x's. X squared, x cubed. So I end up with x cubed plus 3x squared plus 4x plus 12. Which gives me 4 terms We know how to solve this algebraically. We can factor by grouping. Let's see if it works. These guys have an x squared in common, x plus 3 left. These ones have a 4 in common, x plus 3. Okay, this one lets me factor by grouping. If this didn't work, then we'd want to keep going with our rational root theorem, see if we could find something else. Right. But we factor by grouping, we get the x plus 3. X squared plus 4 is left over. This gave me my root of negative 3. But I also need to find when does x squared plus 4 equal 0. We can solve that using square roots. Subtract 4 from each side and square root both sides. Don't forget when we square root, it's plus or minus. And since we have a negative under our square root, we have an I in there. And we can square root 4 nicely. So it's 2i, plus or minus 2i. And we see here too, our conjugate root theorem at work really. We have 2i as a root, it's a complex number. Negative 2i is also a root. And I mentioned this in the conjugate root theorem video, that when we have a conjugate root, that always occurs when we have to take the square root of something, or when we have a complex root, that occurs by square rooting, and we see that here. Okay. We have two roots, positive 2i, negative 2i, our third, and our fourth, which matches our degree. We're done.